comes to defects, we can broadly categorize them in terms of dimensionality. So the first kind of set, and actually it's quite a large set of defects we're going to be talking about, is our 0D defects. So 0D defects are called point defects. So vacancies are one example of those 0D defects. What's a vacancy? It's basically in our lattice, as you can see here, our lattice is all these blue atoms. They're all the same type. So a vacancy occurs when an atom that should be here in our perfect structure is missing. So we're missing an atom. There's nothing essentially that's there. So there's empty space there where if there should be either, basically an interstitial atom or an atom in the perfect crystal, et cetera, et cetera, et cetera. Vacancies are very, very important. We're going to see a little bit later on. Vacancies are how atoms typically diffuse, as opposed to kind of ring mechanism or direct exchange mechanism. So vacancies are extremely important, and they're incredibly important, especially when we get into electrical and optical materials and diffusivity, and again, very, very important. And we can actually calculate what is the equilibrium concentration of vacancies. So you can do actually we'll go through, a little proof right here. So what will be if I have a perfect crystal composed of n atoms and some amount of n vacancies, little n, what is my equilibrium concentration of vacancies as a function of temperature? Well, my total enthalpy change will be my number of vacancies times the energy that I have to input in order to create essentially a vacancy, because it takes energy. I have to remove a vacancy, or remove an atom from here and put it into somewhere else. Usually, it could be in a self-interstitial spot, it could be elsewhere, but I have to move that. I have to put in energy. I have to put in enthalpy in order to form a vacancy. But from that, we also will then create or actually increase the entropy of our system. So we've talked about this before. I believe maybe it's a minus K, but anyways, we'll get in there anyways. K is our Boltzmann's constant. So I'm going to increase the configurational entropy of my system. So that sub C is configurational entropy. Conformational entropy we'll see with polymers, but again, so I could calculate what is the change in my entropy in this system once I create a vacancy. Well, my reference state is what? What is this reference? The reference, if I have a perfect crystal, my number of configurations is just 1. So my mixed state is what is my new number of configurations? Does this look familiar here? This should look like your what? Binomial coefficient. The number of distinguishable ways that we could arrange essentially n atoms and n vacancies on n plus n sites. So that is my delta S. So now we have what this is. We have here, we can basically, kind of ignore you could keep the vibrational entropy, but we can then use Stirling's approximation to deal with that factorial, realizing this here. And we end up, and then we want to kind of figure out, okay, well, this gives us our Gibbs free energy, but we want to minimize Gibbs free energy. So what is our lowest energy state as a function of the concentration of those vacancies? So we're going to take the derivative of this function here with respect to little n, and you eventually get a fraction of those vacancies. X of v is what's my fraction of vacancies? It's my number of vacancies over my total number of sites. So that's the fraction. It should go from 0 to 1. It will never be 1. You will never be able to reach a temperature. Those should be very, very, very low. And when you plot this, you see this kind of exponential relationship. This functional form here, that exponential minus an energy over kT, is a very, very, very common, a very, very important temperature relationship. You hopefully have seen this before if you've looked at any equilibrium constant. So K equilibrium is, so like let's say I have a chemical reaction, for example. I have a chemical reaction of let me do this here. A times A plus B times B goes to C plus D. If I want to do my K equilibrium constant, what is it? It's my concentration of products, concentration of reactants, over concentration of reactants, A, B, B, and that's going to be equal to or proportional to some exponential minus delta G over KT. So hopefully you've seen this in chemistry and other classes before, but this is an example of an exponential temperature relationship, and it's an Arrhenius dependence, an Arrhenius law. And you could plot that and actually see that exponential increase, as you might expect. Typically for metals, you could kind of ignore that vibrational component. But the key thing that we want to see here, and you can actually plot it as the natural, this is not log, this is natural log, not log base 10. And you actually plot this in an Arrhenius graph and actually kind of see that relationship. And most importantly, you could extract some critical information. So the key thing here is we see at every temperature, there is going to be some equilibrium concentration of vacancies. So the equilibrium state of our system is actually one in which vacancies and defects exist. And that the amount of those vacancies will increase as temperature increases, as you see here. So what are some other 0D defects? I can have a vacancy. I could also have a self-interstitial. So an atom is an interstitial site is in these places there shouldn't be atoms. But if I have an interstitial, I'm basically putting in an atom into that site here. So I'm shoving in an atom where it shouldn't be. So let's take a quick caveat before we get into kind of the other interstitials or other 0D defects. So for self-interstitials, I can do the same calculation, and you get a very, very similar relationship. And it's this way for most 0D defects, at least. Well, actually, I should put a caveat there. This relationship holds for defects that are intrinsic defects. Extrinsic defects, you're actually putting in the energy, you're controlling the amount or the concentration of defects that occur. But what do you think is going to be the difference between the enthalpy of formation for a self-interstitial or a vacancy? Which one will be higher? What's going to be harder for a self-interstitial or for a vacancy? The interstitial is going to be way harder, right? Because you can imagine, if I'm just pulling an atom out, I'm allowing essentially this system to basically relax back in once this atom is gone. So the atoms can kind of move in, just relax a little bit here, if you can imagine them with springs. But if I'm putting an atom right here where it shouldn't be, it's pushing out here. So you're creating kind of a high, basically these little like stress states in your system. So that'll be important once we get into defect motion and migration and movement of defects. But anyways, those will be a little bit important later on. But it's going to be much harder to create an interstitial or self-interstitial than a vacancy. But you can do that, and actually there's processes like here. You could increase defects, quenching, irradiation, cold working. So you could create a lot of defects in that manner. What other types of defects are there? So I could have a substitutional impurity. So instead of a blue atom here, so like iron, I could substitute with another atom. Now, typically, again, we're not drawing this to scale, but if you substitute an atom, they're going to be either larger or smaller, and that will also affect essentially like the local stress and strain states there. I can put an impurity atom in here. And again, here we're looking at a smaller atom, so that could be like a carbon. That's not going to affect it's still going to affect essentially the local strain state, but if you put a large atom in there, then that will be problematic as well. So those are all the types of different basically 0D defects that you may encounter. There's one more special one, and we'll talk about that in just a second. But before we get to that, we keep talking about these interstitial sites. And we've talked about intrinsic interstitial sites and extrinsic interstitial sites. So again, we just actually talked about that example of carbon and iron. But how do we actually classify what these interstitial sites are? Well, the way that we typically classify them is via this, basically, what are their number of nearest neighbors? What are the number of atoms, or actually, what is the number of atoms that basically they fit in between those? How many number of nearest neighbors do I have for that interstitial site? So, octahedral sites, tetrahedral sites are some of the most common interstitial sites. So, octahedral site. Each of these black dots is an octahedral site for, what is this structure? Where we learned it last time? FCC. So an octahedral site for an FCC, for an interstitial, is going to be how many coordinated? octahedral, you think 8, but it's actually 1, 2, 3, 4, 5, 6. We need to learn our roots again. So an octahedral sites will be coordinated by 6 different atoms. The octahedral sites for BCC is a little bit more complicated to see, but you can see here 1, 2, 3, 4, 5, 6 right here. So you can still see this. It's still visible, but it's a little bit more difficult to see. Tetrahedral sites. What about tetrahedral sites here? So that will be site right here. So I've got 4. 1, 2, 1, 2, 3, 4, if you can see here. But you can see here. And then, so basically those are some of the sites that we're going to it's going to sit inside. One last type of 0D defects is Schottky and Frenkel defects. So these are pairs of defects. So a Schottky defect is the formation of a pair of vacancies. So these defects, Schottky and Frenkel defects, can only occur in ionic crystals. What's an ionic crystal? NaCl. That's an ionic crystal. CaCl2. What else? I'm trying to think of none. How about CaO? That's an ionic crystal. So when we have ionic bonding, which we talked about, again, you see how this class, it builds and builds and builds and builds, and we're just kind of talking about things that we build upon from the first lectures. That's going to continue on the whole class. This class will make sense at the very end. So that's when I create a pair of vacancies in the anion and the cation. A Frenkel defect, on the other hand, that is going to be basically either an anion or a cation vacancy and corresponding anion-cation interstitial pair. So we'll come back to those a little bit later on, but those are the last pair of 0D defects that we'll see. Now, coming up is one of our most important defects. It's our 1D defects, and it's dislocations. Dislocations are critical to understand essentially the mechanical behavior of a material. So we will be talking about that in the next one. So thanks, and see you then. Bye.